let's walk through an exercise. Exercise 2 on the handout. It's going to be our first example of combinatorics being a use of linear algebra. So let's say we have a bunch of sets, and they are within the first n numbers. So let's say A1, A2, all the way to AM are subsets of n, the first n numbers. So the problem says to show that if we have at least n plus 1 sets within the first n numbers, that we can we can sort them into two groups. Let's say in the first 3 numbers we take the sets 1, 2, 2, 3. Let's say another set is 1, and another set is I don't know, 1, 3. So the claim is that we can take these sets and take 2 groups of these sets in particular that have the same union. So can anyone split these sets into 2 groups that have the same union? Yeah? Yeah?
So it would be 1 and 2, 3, and 2.
Yeah. So this set and this set have union 1, 2, 3. And these 2 sets have union 1, 2, 3. And so we have found 2 groups that have the same union. So how we are going to approach this is to take a vector corresponding to every set. So we're going to look at r to the n. And in r to the n, we can represent each set as a vector as follows. What we can do is, let's say we have n equals 5 and the set 1, 3, 4. What we do with our 5 coordinates is we say 1 if the ith, 1 at the ith index if the ith number, if I is in the set. Yeah, 1 at the ith index if I is in the set. So at the first, third, and fourth positions we put a 1. Everywhere else we put a 0. So then we can form a vector from every set. Let's say that if A is a set, we are going to call this vector V sub A. So we have n plus 1 of these vectors in an n-dimensional space. What does that allow us to say? They're linearly dependent. There's some combination which sums to 0. Yeah. So we can write that there exists some constants ai such that the sum from I equals 1 to m of ai times v sub a sub I equals 0. This is just saying that they are linearly dependent. So what we can do with these is we can sort them in a sense, we can sort them by whether the coefficients are positive or negative. And what I mean by this is, let's take this example. So let's say we have v sub a sub 1 plus 3va sub 4 minus 2va sub 3 equals 0. What we're going to do is we're going to keep all the positive terms on the left side and move all the negative terms to the right side. And that gives va1 plus 3va4 equals 2va3. Now, what would this allow us to say about the unions of a1, a4, and a3? Why?
Because you can arrange vectors to equal 0. Because you can arrange the A1 and 4 vectors to equal like, a certain amount of A3.
Sure. So along this lines of thinking, okay, so let's look at the ith index in each of these sides. So we can denote this by this sub I. This just means the ith coordinate of the vector. If I is in, if this is positive, what does that say about I? Remember that this thing sub I is 1 if I is in the set and 0 if it's not. And what does it say if this term is positive with respect to the union of A1 and A4? Yeah? Why?
Because that would mean that I had to be non-zero, which can only happen if one of them had it.
Yeah. So if this is positive, that means that I is in the union of A1 and A4. However, if this were 0, what does that say? Yeah?
All instances of I are in VA4. All instances of
Well, if I was in VA4, then VA4 would give a positive number. So if this were 0, on the other hand,
the entire thing.
huh?
The entire thing within the parentheses.
Yeah.
Then that would mean that they're not equal on both sides because you still have the other side defined as having an instance of I in it.
I is just any index, not necessarily 1 in A3. I'm just saying, what if it weren't the case that this were positive? If this left-hand side were equal to 0, yeah?
Then it couldn't be in the...
Yeah, it wouldn't be in the union because if this were equal to 0, then since all of the ith coordinates are positive because they're 0, 1 vectors and we have only positive terms on this side, that means that every single entry has to be 0, meaning that I is not in A1 nor A4. And the same can be said of the right-hand side. If this thing is positive, then I is in A3, and if it's not in A3. Meaning that since these are equal, in other words, they're positive at the same time and negative and 0 at the same time, that means that the unions of the two sets must be the same. Okay. So what we are going to do now is do an even stronger statement. We can show that if instead of having n plus 1 sets, we have at least n plus 2, we can show that any subsets of the first n numbers, we can select some of these sets that have this, two groups of the sets such that they have the same unions and they have the same intersections. So here, let's do example again. So let's say we take these 5 sets. So can anyone point out how we can split these into 2 groups which have the same union and the same intersection? Yeah.
3, 2, 2, 3, 2.
These two and these. Yeah, that works. So this group and this group. So what is the union of these two sets? Yeah. And the union of these three sets? The intersection of these two. And an intersection of these three. Empty again. So thus we can say, the problem statement is to show that if we have 5 subsets of the first 3 integers, or in general n plus 2 of the first n, then we can have some with the same intersection and some with the same union. So here's how we can do this. So how can I phrase that 2 intersections are equal in terms of unions? Or how do you phrase an intersection in terms of the unions? Yeah?
I think it's the complement of the unions of the complements.
Yeah. So we're going to use intersections like that. Instead of intersecting sets, we are going to take the union of their complements complement. So how we can do this is we can write the following vectors. So let's take our set 1, 3, 4 again. To take the original problem, the original method, we would write this vector because there's a 1 at the 1, 3rd, and 4th indices and zeros at the others. But now what we're going to do is we're going to use the rest of the entries to encode the complement of the set, which is 2 and 5. So 0 at the first index, 1 at the second, 0 at the 3rd and 4th, and 1 at the 5th. Corresponding to numbers 2 and 5, the complement of 1, 3, 4. So the first thing to show is that these vectors lie in an, well, what we need to have, since we have n plus 2 vectors, what we need is that these vectors lie in an n plus 1 dimensional space. But that is not immediate because there are 2n coordinates in these vectors. So the question is, what can we do to reduce, to constrain where the vectors lie? And so what we can notice is that in our vectors, the first and 6th positions always sum to 1. Why? Yeah? Sure. So if this were 1, this would be 0 by definition. If this were 0, this would be 1 by definition. And likewise, the 2nd and 7th positions always sum to 1, and the 3rd and 8th, and so on. So we can write the equations x1 plus x6 equals 1, and x2 plus x7 equals 1, and so on. So I'm going to write that as x1 plus x6 is x2 plus x7, which is x3 plus x8, and so on, all the way down to x5 plus x10. So how many constraints is this equation? Or, yeah, that's the general question. Like, writing, let's say we write A equals B equals C. Exactly how restrictive is this on A, B, and C? Is the question. So how many things do you need to know are equal? Or how many pairs of terms do you need to know are equal before you can say these are all equal? And what two would they be? Sure. So you only need to know A and B are equal and A and C are equal to know that these are all equal. Similarly, when we have 5 things here, that's only 4 constraints. We need to know that and the first and second terms are equal, the first and third, and so on, all the way to the first and fifth. And in general, writing this for n instead of 5 would be n minus 1 constraints. So that restricts the dimension of the vector space. If we only look at the vector space satisfying this equation, that restricts the dimension. Since we have a 2n dimensional vector space, and we have n minus 1 constraints, so to speak, that gives that our total dimension of the vector space is going to be n plus 1. So since we have n plus 1 since we have n plus 1 vectors, since we have n plus 2 vectors in an n plus 1 dimensional space, that means that our vectors are linearly dependent again. So we do what we did last time. So since they're linearly dependent, we look at some linear combination of them that equals 0. And what did we do last time with our linear combination? How do we rearrange this? What terms do we move to the right-hand side? Yes. So we have sum of ai v ai for some set of indices, let's say I1, where these are all positive, equals another sum for I in a different set of indices. We can write this. So if we look at the first n entries of the vector, what does that give us when we say that these are equal? It's the same thing as last time. What that says is that the unions of the sets are equal. But if we look at the last n entries, what does that provide? Yeah? Yeah, the intersections are equal because that says that their unions of the complements are equal, and so complementing that, the intersections are equal. So yeah. Now we move to things which are much harder to approach without linear algebra. In particular, we are going to prove Helis Theorem, which is an interesting statement in its own right. So if we have a convex set, what's a convex set? First of all, what's the definition of a convex set? Yeah?
It's a set where every line thing that has to be 2 points in the set, and never leaves it.
Yeah. So if we have any 2 points in a convex set and we connect them via line segment, all points on the line segment are within the set. So for example, this square is a convex set. Is this a convex set? Is this a convex set? Why? Yeah? Yeah, if we take the bottom 2 vertices, then here's a point on the segment that lies outside the set. So the ultimate goal, okay, first let's talk about Radon's theorem, which we're going to prove first. Radon's theorem says that if we have n plus 2 points in n dimensions, then we can split them into 2 groups who have intersecting convex holes. So first I'll need to talk about what a convex hole is. The convex hole of a group of points is the smallest convex set containing them. So the convex hole of these 5 points is this quadrilateral. Okay, wait, I shouldn't draw segments. So, let's say I have these points, label them. So what are the vertices of the convex hull here? Yeah? Yeah. If we connect 1, 4, 5, and 6, this is the convex hull, the set of points within this polygon. So the claim is that any n plus 2 points in n dimensions can be split into two sets with intersecting convex hulls. So how that works is, let's say we have 4 points in 2 dimensions. Then I claim I can partition these points into two sets such that their convex hulls intersect. Namely, if we take the convex hull of these 2 points and we take the convex hull of the rest of the points, they intersect right here. So how can we do it for example, these points? Yeah?
The big triangle and this one and the ending point of the other.
And the other is just this one. So the convex hull of these 3 points is the triangle highlighted. The convex hull of this point is just itself, and these intersect at the point. So let's just prove this without any linear algebra for 2 dimensions, which should not be hard, as I've more or less shown all the cases. So first of all, any 3 points, well, we can, case 1, they're all on a line. What do we do? As in, how do we partition these? Yeah?
The leftmost one.
Yeah?
And the second from right one.
Sure, we can take these. We can take group 1 is these 2 points, and group 2 is these 2 points, and their convex hulls intersect because, well, they just intersect at this whole thing. That's that. So let's say we're dealing with points that aren't on the line. So then we can take 3 points on a triangle, and the 4th point is anywhere else. Well, these. No, let's do it this way. So we have 3 points that aren't collinear, and we can then do casework based on the number of vertices in the convex hull of the new thing. So if there are 3 vertices in the convex hull, how do we partition it? We just connect them to form a triangle and take this point again. If there are 4 vertices in the convex hull, the partitions we can take are these vertices, and the diagonals will intersect. So yeah, that's that for 2 dimensions. But we are going to show this for n plus 2 points in n dimensions. So first thing to do is describe a convex hull using linear algebra. Let's go to 2 dimensions for that first. So if we have this point is a vector v1, this point is a vector v2, and this point is a vector v3, I claim that the convex hull of the 3 points is the set of numbers that can be written as a1 v1 plus a2 v2 plus a3 v3, where a1 plus a2 plus a3 equals 1, and all of these are positive, or non-negative, that is. So I claim that this is the convex hull of v1, v2, v3. A way to think about this and this is a weighted average of v1, v2, and v3. Or alternatively, this is the center of mass of three masses where located at v1, v2, and v3 with weights a1, a2, and a3. In general, how we can think of the convex hull for n points is we look at all possible numbers of the form a linear combination of the vectors where the sum of the coefficients is equal to 1 and all of the coefficients are positive. So that is how we can look at the convex hull with linear algebra. So now what we want to show is that for any for any set of points, we can partition them into two groups whose convex hulls intersect. So what we're going to need to do is to show first that any n plus 2 vectors are so-called affine dependent. What this means is for any if we have vectors if we have vectors v1 all the way to vn where there is some linear combination of them that is equal to 0, where all the coefficients, if you take their sum, that equals 0, then we say that the vectors are affine dependent. So let's look at this in 2 dimensions. So for one, let's say we look at the vectors 1, 0, 0, 1, and 1, 1. Are these affine dependent? Well, here's how we can do this. Let's say we had a linear combination that sum to 0. Let's say that's a times 1, 0 plus b times 0, 1 plus c times 1, 1 equals 0. So looking at the first coordinates, what do we get?
2, 2. If you set A, B, and C all to 1, you get 2, 2.
Yeah, but if I want them to be 0, 0, what does that tell us about A, B, and C? And what does the first column tell us about A, B, and C? Yeah?
Is negative c.
Yeah. That gives A is equal to negative C. The second column gives what? Yeah. B equals negative C. And so if we then sum up all of these, we get that A plus B plus C is equal to A plus A minus A equals A. So we can't have that their sum is 0 unless they all are 0. And that's not what we want. So these 3 points are not affine dependent. Let's look at 3 points which are affine dependent. I claim that the points, let's say, 0, 1, I don't know, 1, 0, and, nah, I got it. Here's better, 1. So let's say we look at the points 3, 0, 0, 6, and 2, 2. So I claim that these points are affine dependent. Why? What coefficients do we need? What coefficients do we actually need? Okay, so I think what we can do is take 1 times the first vector plus, let's say, -3 times 2, 2, plus 2 times 3, 0. So these vectors, well, first of all, 1 plus -3 plus 2 is what? Yes. So that satisfies the sum of coefficients condition. So what do we have right here? What is the first coordinate of their sum? Yeah. Because that's 1 times 0, which is 0, plus -3 times 2, which is -6, plus 2 times 3, which is 6, and that gives 0. Similarly, what's the last coefficient? Yes. That would be 6 plus -3 times 2 plus 2 times 0, which is 6 minus 6 plus 0, which is 0. So these 3 points are affine dependent. What's so special about them is that they lie on a line. In general, the interpretation of affine dependent geometrically is if we have affine dependent vectors in an n-dimensional space, that means that they're degenerate in the sense that they happen to coincide on a certain thing. Like, let's say if we have 5 vectors, what it means for them to be affine dependent is that they lie on a 4-dimensional space. Or alternatively, what it means for 4 vectors to be affine dependent is for them to lie on a plane. 4 points normally don't lie on a plane, but if they did, they would be affine dependent. So, since we have, if we're returning back to Radon's theorem, we have n plus 2 points. They're in an n-dimensional space. So I claim that they're affine dependent. And here's how we can see this. Let's say we have 4 vectors in a 2-dimensional space. Say 0, 3, I don't know, random numbers, random-ish. So if we have these 4 vectors, I claim that they must be affine dependent in a 2-dimensional space. In other words, that the 4 points must lie on a plane. And here's why. To show this symbolically, let's say that for every vector I have right here, I add the coordinate 1. So now they're all in a 3-dimensional space. And still have 4 vectors, which is more than 3. They must be linearly dependent. And if they are linearly dependent, we can write sum of ai times vi equals 0. So if we look at the last coefficients, what does that say? All right, the last coordinates. Yeah?
The coefficients of all have to add 0.
Yeah. So if we look at the last coordinates, that gives sum of ai times 1 equals 0. Or in other words, the sum of coefficients is 0. But if we look at everything but the last coefficients, what does that say? I should call these vi prime, because they're not the original vi. So everything but the last coordinates is what our original vectors were, right? So if this combination is 0, that gives us that ai vi is equal to 0. And so generalizing this proof, n plus 2 vectors in an n-dimensional space are always affine dependent. So yeah. And now we can prove Radon's theorem as follows. Say we have some combination of our n plus 2 points, v1 through vn, that is an affine dependent combination. So let's say 1 times v1 plus 3 times v2 minus, let's say, 6 times v4 plus, what's it, 2 times v5. So let's say that this equals 0. So I should have some negative coefficients. So what we should do is change this to that. Okay, so say we have this. So what we're going to do is apply the idea of moving positive terms to one side and negative terms to the other side again. So what does this say about our two sides now? The sum of the signed coefficients was 0, so the sum of the new coefficients on each side is the same, because we had the positive terms minus the negative terms is 0. In other words, the positive and negative absolute values were equal. So now we have that the sum is the same. What we're going to do is divide by the sum of coefficients on either side. So that's dividing by 4 here and 4 here. So now that the sum of the coefficients on each side is 1. So do you remember what I said about convex sets and their linear algebra definition? That would be the convex whole of some vectors vi is the set of points of the form this, where the sum of ai equals 1 and all the ai are positive. Well, that is true now. The sum of the coefficients here is positive. And all the coefficients are positive and the sum is 1 because the sum of the coefficients in the numerator is equal to the denominator. And thus, this implies that the convex whole of v1 and v2 contains this point. And the convex whole of v4 and v5 contains this point. And since they're the same point, that means the convex whole of v1, v2, and v4 and v5 intersect. Yeah?
How did we get that coefficient?
The sum of coefficients on either side is the same. That comes from this condition. Since we have 4 vectors, we can say that there's an affine dependent combination of them. In other words, there's a combination such that 1 plus 3 minus 2 minus 2 is 0 in this particular case, or the sum of coefficients is 0. And if you move the negative terms to the right-hand side, the sum of the positive coefficients was negative the sum of the negative coefficients, meaning that the sum of the coefficients on either side is the same now. So now we have that any set of n plus 2 points can be partitioned into 2 sets with intersecting convex holes. And that is Helis theorem. Now, Helis theorem implies a really neat theorem called Radon's theorem. And here's what that says. So I'm going to take the 2-dimensional case. If we have a bunch of 2-dimensional sets, and they're all convex, let's say that any 3 of them intersect at a point. Then all of them intersect at a point. So any 3 sets do indeed intersect at a point. For example, this set, and this set intersect right here. And it is indeed the case that they all have a point in common. So in general, the statement is if we have a bunch of sets in n dimensions and any n plus 1 of them intersect at a point, then all of them intersect at a point. So let's show that. So the first thing I'm going to do is claim, so if we have our n dimensions, we're in R to the n, and we have n plus, if we have more than n plus 1 sets. Let's say we have m is at least n plus 1 sets, and if we want to show that all of them intersect at a point, if any n plus 1 do, I claim that it suffices to show this for m equals n plus 2. And here's the argument. It's by induction. So let's say we've shown this. Now to show it for all m, well, we've done it for m equals n plus 2. So let's say we want to go from m to m plus 1, where m is at least n plus 2. So how we can do this is, let's take our sets A1 all the way to A m plus 1. So we have that any m of these intersect at a point. In particular, if we take what is it? If we look at A1 through AM minus 1, and then we look at the set AM intersect AM plus 1, we now have m sets. And so what we want to show, and we only need to show that any n plus 1 of these intersect at a point now. So if we have n plus 1 of these sets, well, by definition, any n plus 1 of these sets intersect at a point. So if we, however, look at AM intersect AM plus 1, intersect some n of these, and we want to show that this is non-empty, well, now we can use the fact that we've proved it for m equals n plus 2, because now we have n plus 2 sets. And so thus all we need to do is show that if we have n plus 2 sets, that they all intersect at a certain point. So here's how we're going to do this. So let's say I take some convex sets, A1, A2, A3, and A4. Now, for every, I'm going to draw this part slightly differently. Now, we have that every 3 of these sets intersect at a point. So let P1 be a point where all sets but A1 intersect. P2 be a point where all sets but A2 intersect. P3 be a point where all sets but A3 intersect, and finally P4 be a point where all sets but A4 intersect. I'm going to move this point a bit. Yeah. So now what we want to do is show that all these sets intersect. Now we have n plus 2 points. So we can then use Radon's theorem to show that some 2 of these, I mean, you can split these into 2 groups whose convex holes intersect. This was not drawn so well, was it? P1 should be in. Okay, I'm going to change this a bit. Darn, this is messy. So let's say that that is how our sets work. So yeah, P1. There we go. That should be better now. Yeah. Sorry for the very messy diagram. So let's look at where. Let's look at the point that Radon's theorem gives us. Namely, this is a point in the convex hull. This is a point in the convex hull of some group of points and in the rest of the points. So let's say CH of something is the convex hull of it. So this point, let's call it X. This is X, is in the convex hull of P1 and P3, as well as the convex hull of P2 and P4. And just as a reminder, P2 is a point common to all sets but A2. So I claim that X is in all the sets. So let's show this, for example, for A1. So which of these points are contained in A1? By definition?
P2, P3, P4.
Yeah, P2, P3, P4. And so if we look at the convex hull formed by that doesn't contain P1, P2 and P4, then why must X be in A1 if we look at this? Yeah, P2 and P4 are in A1. So since A1 is a set containing P2 and P4 by definition of a convex hull, it must contain the convex hull of P2 and P4 and thus must contain X. Now if we look at A2, it contains P1, P3, and P4. And thus by definition it then contains the convex hull of P1 and P3. And thus X is in the set. In general, for AI, if we look at the convex hull that doesn't contain PI, then by definition a convex hull, all points in that would be contained in AI, and then X would be in AI. So thus we found a point common to all the n plus 2 sets, and therefore we have so-called Helis Theorem, which states that any n plus 2 convex sets must intersect if any n plus 1 of them do in n dimensions. And I think right about now is break time. So see you after the break. So let's talk about a result of dent. So I forget the word for this. It's scissors congruent. So two shapes are scissors congruent if you can like cut them up and reassemble them into another and into the other. Some restrictions: your cuts have to be straight. So for example, this square and this parallelogram are scissors congruent if we're like, these are equal and this is a 45-degree angle and that's equal here. Because, well, I just drew the cut. You can cut this and reassemble like that. Scissors congruent. Equidecomposable. I like that word more. So, yeah, any two polygons in the plane can be, if they have the same area, can be cut up and reassembled into one another. We are going to look at this question in 3 dimensions. So the goal is to show that if we have a cube and it has the same volume as a regular tetrahedron. How do you draw a regular tetrahedron well? Say I start with the triangle. So if we have a regular tetrahedron and a cube with the same volume, the goal will be to show that they are not actually scissors congruent or equidecomposable. And here straight cuts are replaced by straight slices with a knife. So yeah. So the guy who first showed this was named Den. He in particular showed that if two equidecomposable polyhedra have the same volume and the same so-called Den invariant, then they are scissors congruent, and otherwise they aren't. We're going to be studying this with a simplification of the Den invariant. That's just easier to handle. So, yeah. First, let's talk about what a linear transformation is. So if we have two vector spaces, V and W, a linear transformation is a map from V to W such that T of the sum of vectors is equal to the sum of their images, and T of a scalar of a vector is equal to the scalar of T of the vector. So that's what a linear transformation is. It basically is a map from one vector space to another that preserves the structure of the vector space. So for example, here's a linear transformation from r squared to, say, r cubed. We can map xy to, I don't know, 2x minus y, y, x plus y. That is one example of a linear transformation because it satisfies these two properties, which can be checked fairly easily. So, here is a thing. So we're going to be working with a vector space where we're so the scalars in a vector space, these a's and b's and whatnot, we could consider them to be real numbers, but we can restrict them to be any so-called field. Fields basically where you can do addition, subtraction, multiplication, and division. So instead of using the real numbers for this problem, we're going to use our scalars in the rational numbers. So, first question, first part of this. So the dihedral angle between two faces is, in a polyhedron, is the angle between them. Angle between the planes containing the faces. So the dihedral angle of a tetrahedron, I guess I'm going to label these. So if we let M be the midpoint of BC, the dihedral angle, I guess, would be AMD. So first we're going to find this on the tetrahedron. So can anyone state the simple embedding of a tetrahedron in three-dimensional spaces, in a three-dimensional space, coordinate-wise? You can also think of this one as, if we have a cube right here, let's do it this way. If we have a cube, and let's label these vertices, can anyone name 4 vertices that form a tetrahedron? Regular tetrahedron. Yeah? Yes. A, F, C, and H have the property that they are 4 vertices, the distance between any 2 of which is square root of 2. So they form a regular tetrahedron. If we look at this in coordinates, that says that the following 4 points form a tetrahedron. So the cube is just the set of points where the coordinates are plus or minus 1. So if we look at these ones in particular, here are 4 vertices that form a regular tetrahedron. You can check that the distance between any 2 of these is square root of 2, aka each of these 2 root 2, aka each of these differ in 2 coordinates. So now we are going to find angle AMD. So let's say that this is A and D, and here's B and here's C. Should I do it this way? No, I'm going to swap this. So let's say that these are A and D, B and C. What is the midpoint of B and C? What's this coordinate? Next one. Next one. Yeah. We can see this just by taking the average of each of these coordinates. And that gives this. So we then, okay, so does anyone know how to take the angle between 2 vectors by any chance? Yeah?
You could like use a lot of cosines, so you could do like MA times N take a dot product.
Yeah, dot product is what I'm looking for. So if we have 2 vectors, u and v, then the angle between them satisfies that the dot product of the 2 vectors is equal to the magnitude of u times the magnitude of v times the cosine of their angle. Now the dot product is formed by taking the product of the first 2 coordinates plus the product of the second 2 coordinates, and so on. We're going to see this right here. So what we want is the angle between vectors a minus m and d minus m. So what's a minus m? To what? One minus 0 is 1. 1 minus 0, again 1. On the other hand, d minus m is equal to yeah. So the dot product of these 2 is going to be the product of these plus the product of these plus the product of these. That's how it works. So the dot product, the dot product is then 4 minus 1 minus 1 equals 2. Yeah. And okay, so for these vectors u and v, this is 2. 2 equals, okay, we need magnitude of u and magnitude of v. What is the magnitude of this? Pythagorean theorem in 3 dimensions gives, yes, square root of 2 squared plus square root of 2 squared plus 1 squared plus 1 squared, square root of 4 plus 1 plus 1 squared is 6. Magnitude of the other thing is square root of what? Yes. So we have this, so cosine theta is equal to 1/3, or theta is equal to arc cosine of 1/3. Okay, so first of all, claim 1. I'm not going to prove it now. I guess I'll postpone the proof of this to the end of this or never. So theta over pi is irrational. I'm going to take this as a fact for now. We may prove it later. I don't know. So yeah. And what we can do with that is say, I claim that where we are again going over the rational numbers, I claim that, well, we're going to assume what's called the axiom of choice and show that there's a linear transformation from R to R where T of pi is equal to 0 and T of, let's give this guy a name. Let's say, oh, I say theta. I don't want theta. Let this be alpha. Okay. Let alpha be arc cosine of 1 over 3. So I claim that there's a linear transformation that satisfies this. And basically how we construct this linear transformation is we choose where to send stuff one by one. So this tells us where to send anything of the form p alpha plus q pi, where p and q are rational numbers. So then we can take a number that is not of this form, say b1, which is not of this form, and then we can say that T of b1 is, let's let it be 0. So let T of b1 be equal to 0. Then now what we can do with our linear transformation is we are able to tell what anything of the form p alpha plus q pi plus r1 b1, anything of this form, we are able to tell, and we are able to give the value of. Why is this? I mean, if we have this, what can we write that as? Yeah. So by additivity, we can just split this up term by term. And then by the multiplicative thing, this is p t alpha, which is 1 plus 0 plus 0. So that's just p. So now we know anything of the form p alpha plus q pi plus rb1. So then we're going to take a b2, which is never of this form, and then we can set T of b2 to be 0, and then we'll know anything of the form p alpha plus q pi plus r1 b1 plus r2 b2. And then what we're going to do is take b3, not of this form, and so on. We can do this forever, assuming the so-called axiom of choice, namely, if you have a bunch of sets, you can pick one element from every set. The sets we're picking are numbers not of these form, basically. So that assumes the axiom of choice. We're going to modify this proof later to not use the axiom of choice, but for now, let's just take that there exists a linear transformation T like this for granted. So now what we are going to look at is the following thing. For an edge E of a polyhedron, let L of E be its length, and let theta of E be the dihedral angle. So we are going to look at the following function of a polynomial, of a polyhedron. Let d of p for p of polyhedron be equal to the sum over all the edges in P of the length of the edge plus, times T of theta of the edge. So let d of p be this weird quantity. So let's do some stuff. First, what is d of a cube? So to evaluate d of a cube, we have a sum over the edges. There are 12 edges. So that's 12 times the length of any edge. Let's say that's the side length of a cube. Let's call that S. Times t of the dihedral angle of a cube, which is what? 9 degrees. Pi over 2. Okay. So what is t of pi over 2? Well, we can write pi over 2 as 1/2 pi. And then what can we do with that? Yeah, we pull the 1/2 out. That gives 1/2 t of pi, which we know is 0 because t of pi was defined to be 0. However, if we want d of a tetrahedron with side length s, that would be, well, there are 6 edges to sum over, all of which have the same length and angle. So that's 6 times the side length of the tetrahedron times t of the dihedral angle of a edge, which is alpha, and then by definition we say that this is 1. So the most important thing to note here is that d of a cube is equal to 0. Let's say a cube, let's call a cube q. So dq is always equal to 0, whereas dt, where t is a tetrahedron, is always not equal to 0. And so I claim that this means that they are not equidecomposable. In other words, they cannot be cut from one to the other. Yeah? Dihedral angle. So if we have 2 faces of a polyhedron, the angle that the faces make is going to be what we call the dihedral angle. Yeah. So the most important, the important thing about d of p, what makes it so special, is that I claim if p can be cut into pieces p1 and p2, then d of p1 plus d of p2 is equal to d of p. And here's why. So let's say we cut a polyhedron. Cutting a polyhedron is hard to draw, so I'm not going to draw it. Okay, I'm going to draw part of it. Let's say we have an edge in our polyhedron, and we make a cut. Let's say like this. So for every edge, the original value that it contributed to d of p was its length times t of theta of the edge. But now if we cut it, the length splits into 2, right? But the angle remains the same. So if an edge E1 splits into E1 plus E2, the length of E is equal to the length of E1 plus the length of E2, whereas the angle of E remains unchanged before and after the cut. No, equals. Okay, so that means that this quantity of the edge before and after the cut stays the same. So now all we have to do is show that the edges we create, such as this edge, don't do anything to this quantity. So let's say that we create an edge by making a cut. So let's say we have a corner like this, and we created an edge by making a cut right here. Darn, I should draw this like, I'm going to do it like this. So let's say we make a cut right here. So we have a new edge formed by the cut. Let's look at this edge in particular. And it becomes an edge of both P1 and P2. And let's say that this angle of the cut, this angle is equal to theta. Okay? So this new edge, let's call it E. Well, in D of P1, E contributes the length of E times T of theta. Or let's call this theta 0. And in P1. But in P2, what the edge contributes is the length of E plus T of the remaining angle, which is pi minus theta. So what do these sum to? That's L of E times T of pi, because these sum, T of pi because these sum to pi, and T of pi is 0 by definition. So every created edge contributes 0, and every edge that we split by making a cut contributes 0 to the final value of dp. And thus, we know that the quantity, when we're doing the cutting process from the cube to the tetrahedron, we know that the sum of d of all the pieces is always preserved. And thus, since the cube and tetrahedron had different values, that means that one can't be cut into the other. So now, the thing we want to do, the first thing we want to do is remove the use of the axiom of choice. We needed the axiom of choice to get a linear transformation like this, but we're going to get around using that. And here's how. Let's say we have a cube, and we managed to cut it from a cube into a tetrahedron. Now how do you draw a capital theta? I think it's just like that. Nothing more to do. So let capital theta be the set of angles that come up when we try to cut the cube into the tetrahedron. Let theta be the set of angles that come up, and then what we can do is instead of t being a transformation from R to R, what we're going to do is let t be a transformation from the span of theta to R. And what the span is the set of things which are of the form, it's the set of linear combinations of the angles in theta. In other words, a set of stuff of the form sum over theta in capital theta of q times theta, and q sub theta times theta, where q sub theta is a rational number. So if we let this be the case, then span of capital theta is a finite dimensional space. And what we can do instead of trying to map things one by one, since this is a finite dimensional space, we can take some stuff that's generated, like pi a and a bunch of other angles, pi alpha b1, b2, and so on. But now we can terminate them off. So if these are all linearly independent and they generate span of theta, then we can just assign these to map to 0, 1, and whatever else we want. And then we have a linear transformation that shows that we cannot rearrange the cube into the tetrahedron. So what time is it? Okay, so let's see. So in the proof, I assumed that alpha over pi was irrational, so that setting the value of t of pi to 0 doesn't mean that t of alpha is 0. Do people... raise your hand if you want to actually see the proof that alpha over pi is irrational. Like, it's fairly interesting in its own right. Sure, I'll do that. So I'm not erasing this. I'll move over here. So what we need to define are so-called the Chebyshev polynomials of the first kind. I don't think I can spell Chebyshev on my first try, so I'm just not going to. How these work is we are going to show that there's a polynomial t sub n such that t sub n of cosine theta is equal to cosine n theta. Now you can do this with repeated trig identities. But here's a particularly nice way to define it. So what's t sub 0? T sub 0 of theta is equal to t sub 0 of cosine theta is going to be equal to cosine of 0 theta, which is what? Yeah. So t sub 0 we set to be 1. T sub 1 is going to be what? Yeah. In particular, that means that since we want t sub 1 to be a polynomial, we're going to just say that in general, t sub x is equal to x. Or t sub 1 of x equals x. T sub 0 of x equals 1. And now what we can do is we are going to define t sub n recursively. So, first of all, via trig identities, okay, here's one thing to know. So this is, what's it called? Sum to product, I believe. No, product to sum, I guess, since we're going this way. So this trig identity, I guess, if you don't actually remember this by heart, what you can do to show this is expanding cosine a minus b gives cosine a cosine b plus sine a sine b. And cosine a plus b gives the same thing with a minus. So when you add that up, these terms cancel and you just get 2 cosine a cosine b. Where's an eraser? There's an eraser. Okay. So plugging that in right here would give 2 cosine. Okay, we're going to specify that 2 cosine theta times cosine n theta is equal to what? Does anyone remember this enough? It's cosine of the difference plus cosine of the sum. So that would be n minus 1 theta cosine n plus 1 theta. So now if we know t sub 0 all the way to t sub n, and we want to get t sub n plus 1 via recursion, what we can do is we can write that this is 2 cosine theta t sub n of cosine theta equals equal to t sub n minus 1 of cosine theta plus what we're looking for, which is t sub n plus 1 of cosine theta. So if we let cosine theta be x, because I don't want to write it so much, that just becomes 2x tn of x minus tn minus 1 of x is tn plus 1 of x. So that is how we can compute t sub n recursively. So in particular, let's do it with this example. So we have that t sub 0 of x is 1, t sub 1 of x is x. Let's plug that in here for n equals 1. So 2x, what's t sub 1 again? That's x. So 2x squared minus t sub 0, which is 1, equals t sub 2 of x. If we wanted to plug in cosine again, that becomes 2 cosine of theta squared minus 1 equals cosine 2 theta, which is indeed true. So yeah, this is our, so this is one way, and so as opposed to this definition, actual recursive way to write what t sub n is to say t sub 0 is 1, t sub 1 is x, and then you recursively define this polynomial stuff. So yeah, what we are trying to show, when we say that alpha is irrational, that means that we are trying to show that cosine of p over q alpha, if p over q alpha can never be equal to pi, which is what we're trying to show, we're trying to show that this is never equal to 1, or let's say 2 pi. Yeah. So we want to show that this should never be able to be equal to 1. Now what we can do with that is say, no, let's say cosine n alpha should never be equal to 1. It suffices to show this, because if alpha were equal to, if alpha were equal to p over q pi, then multiplying by q alpha equals p pi, multiplying by 2q alpha equals 2 pi times p, and taking cosines of both sides give cosine of alpha would then be equal to 1. So if cosine n alpha is never equal to 1, then alpha can never be written as p over q pi. So what we want to show is, in other words, that t sub n of cosine alpha is never equal to 1. Does anyone remember what cosine alpha was? Yeah. So we want to show that t sub n of 1/3 is never equal to 1 for any n. Okay. So here's how we can do that. So let's look at the leading term of t sub n. So let's write down again what they are. T sub 0 equals 1, t sub 1 equals x, t sub n is equal to, or t sub n plus 1 is equal to 2x t sub n minus t sub n minus 1. So the leading term of t sub n is going to be always equal to 2 to the n x to the n. And this is because the leading, no, 2 to the n minus 1 x to the n. And this is because, well, the leading term of t sub 1 is indeed this. That would be 2 to the 0 times x to the 1. And to get to t sub n plus 1, this is a lower degree polynomial than t sub n, so we don't care about it. And then when we multiply by 2x, that gives this thing by induction. So this will always be the leading term of t sub n. So if we wanted that to be equal to 1, we would have 2 to the n minus 1 times 1/3 to the n plus a bunch of other stuff equals 1. And now the bunch of other stuff is going to be like a sum of some coefficient times 1/3 to a smaller power than n, abusive notation. But if we then we can then multiply, okay, let's say 3 to the I, right? But then we can write this as a times 3 to the n minus 1 minus I times 1/3 to the I. No, 1/3 to the n minus 1, right? And so we have some integer coefficient times 1/3 to the n minus 1. Another way, so that becomes this. Another way to think about it is basically 1/3 to the n is 3 to the negative n, so the term with lowest degree is 1/3 to the n. And after taking that out, everything else is something times 1/3 to the n minus 1. So we have this equation. Let's multiply by 3 to the n. That gives 2 to the n minus 1 plus 3a equals 1. Did I want that? No, I didn't want that. Oh. Yeah, I should make this 0. Okay. It's equivalent anyway. Yes. Okay, much better. So, why can't this be true for integers a and n? Yeah? Yeah. This is not divisible by 3. This is divisible by 3. So they can't sum to a multiple of 3. And thus, alpha for pi is always irrational. So yeah. That's that. How much time do we have left? Okay. Well, we can try to get this next problem done within time. What should I do? I'll just go with exercise 7. It's often just called the Oddtown theorem. It's a very classical result in linear algebra applied to combinatorics. So the claim is that if we have a town called Oddtown, and there are many clubs in this town, and any club has an odd number of members, but any two clubs have an even number of members in common, then the number of clubs in Oddtown is at most the population of Oddtown. That's the claim. So to do this, other things. So in the equidecomposability problem, we looked at using Q instead of R for coefficients. Here we're going to do something along even further. So we are going to talk about, we are going to work in this set called the field of order 2. I don't know if there's a better name. It's basically the set of even and odd, which we often denote as the set of 0 and 1. Another way to think about this is the set of numbers mod 2. So they're equipped with your everyday operations on even and odd. Like, for example, even divided by odd is even. And odd divided by odd is odd, or odd plus even is odd, and whatever. So we're going to be working with these for coefficients as opposed to real numbers or rational numbers. So the statement, again, is that any club has an odd size, whereas any two clubs have an even intersection. Then if Odd Town has n people, the claim is going to be that there are most n clubs. So, do people know matrix multiplication to some extent? Let's say I'm taking these matrices. I don't know. 0, 1, 1. Do people know how to multiply these? Okay. Here's how it works. So an m by n matrix is a matrix with m rows and columns. Matrix multiplication is always going to be from an m by n matrix times an n by p matrix, and it's always going to produce an m by p matrix. So the number, in other words, the number of rows in this thing has to always equal, no, the number of columns in this thing always has to equal the number of rows, and yeah. So this is a 2 by 3 times 3 by 1, so we're going to get a 2 by 1 matrix as the result. And how it works is you take a column, a row in the first matrix and a column in the second matrix, and you take their dot product, and that's how you get each entry. So the thing corresponding to the entry right here is the dot product of this row and this column, which is 0 times 1 plus 1 times 2 plus 1 times 3, aka 0 plus 2 plus 3 is 5. The entry right here is 2 times 1 plus 0 times 2 plus negative 1 times 3, or 2 plus 0 plus minus 3, which is negative 1. So more practice. What is the product of these two matrices, let's say? So the first entry is going to be the product of the first row and the first column, which is 1 times 2 plus 1 times 2, which is 4. Yes. So what's this entry? Yes. That's 1 times 1 plus 1 times 3, which is 4. What's this entry? Yes. That's 0 times 2 plus negative 1 times 2, which is negative 2. This entry? Cool. That's 0 times 1 plus negative 1 times 3, which is negative 3. So what we're going to be doing is taking the following matrix. It's going to be an m by n matrix, and here's what m and n are. I should draw it more vertically. Not horizontally. Okay, so m is the number of clubs, and we are going to have m rows. We're also going to have n columns, and n is going to be equal to the number of people in our town. And how we're going to form this matrix is every column corresponds to a person, every row corresponds to a club, and we're going to say one in a particular place if the person at the location belongs to the club at the location. Whereas if a person is not in a club, we're going to say that the entry corresponding to the person in the club is 0. So let A be this matrix. We are going to multiply A by itself in the following way. we are going to take A times AT, where AT is A transpose. How do you transpose a matrix? What you do to transpose a matrix is you flip it across the diagonal, where the diagonal is the diagonal containing the top left entry. So that gives the matrix 1, 2, 3, 4, 6, 5. So what is the transpose of this matrix? Cool. So it's denoted like that. So we are going to look at A transpose, and remember we're working where 1 and 0 correspond to odd and even. So A times A transpose. What that looks like is a product like this, where this is an M by N matrix, and this is an N by M matrix. So for every row and every column, we're going to look at their dot product. Every row and every column correspond to a club. So if these rows and if this... So, what?
Isn't that row like corresponds to that row once you transpose?
Well, I kind of drew them like that. I guess they don't have to be. But like, if the row and the column I'm looking at are the same, in other words, if the entry is along the diagonal in the product, that means we're looking at the dot product of a club with itself. So what's that going to be? Given that the size of any club is odd, what's the dot product of the vector corresponding to a club with itself going to be? And why is that? Yeah, when you're taking the dot product of, let's say, this vector with itself, you're just taking 1 times 1 whenever there's a person, that's just 1, and 0 times 0 whenever there isn't a person, that's just 0. So when you add that all up, you get an odd number, which means 1. So the final product is going to have 1s along the diagonal. Now, what if we take rows, the dot product of a row and a column that do not correspond to the same club? And why is that?
It only gives you 1 for both ones, so it has to correspond to each other. So it has to be.
Yeah. So, the dot product, when you're taking it, you will only get a 1. And a 1 corresponds, you're going to get a sum of a bunch of terms, and one of those terms is going to be 1 if and only if the person is in both clubs, because that's 1 times 1. But if the person isn't in one of the clubs, it's either 1 times 0, 0 times 1, or 0 times 0, all of which gives 0. So the dot product of two vectors tells you, two different vectors tells you the parity of their intersection. And since that's even for the rest of them, you get this matrix. Does anyone know the name of this matrix? Yes, identity. And that's because multiplying it by anything gives itself. The identity matrix doesn't change the matrix you're multiplying it by. So we have that A times A transpose is equal to the M by M identity matrix. Let's denote that IM. So the rank of a matrix, that's defined to be the dimension of the span of its rows, which also happens to be equal to the dimension of the span of its columns, which I'm not going to show. So what's the rank of the I sub m? The dimension of the span of the rows of I sub m. So the rows are like 1, 0, 0, 0, 0, 1, 0, 0. Yeah, it's going to be m, because these vectors span just r sub n. So if we look at the rank of both sides, the rank is going to be m. Now, the rank of a product of matrices, I'm not going to show this, but it's the rank of AB is going to be less than or equal to the rank of A, and it's going to be less than or equal to the rank of B. What we can say for this product is that the rank of the product is going to be less than or equal to the rank of A and now the rank of A is at most what? I mean, the rank is the span of all the rows, and since there are m rows, it's at most m. But the rank also happens to be equal to the dimension of the span of all the columns, so it's at most n. Did I do that right? Yes. No, I didn't do this right. Sign wrong. I think. Yeah. So this thing is going to be at most n. So we can then conclude that n is greater than or equal to m by looking at the ranks. AKA, the number of clubs in Odd Town is at most the number of people in Odd Town. Now what time is it? Oh, class is over. So, thank you.